Lecture 1 on linear algebra, solving systems of linear equations. So what we'll look at is we'll look at systems of equations and their solutions, augmented matrices and row operations, a little bit about vector notation in the algebra of vectors, and then finally reduced row echelon form. And can columns be moved? And if you have the RREF, can you figure out what the possible solutions are? So this is what a system of equations, right? A linear system of equations. This is an example of that here. So what do we have here? We've got three variables, x1, x2, x3. We have a bunch of coefficients, the 2, the 8, the 3 in the first row. And so my variables are just multiplied by constants, and you add them up and you get more constants. The variables, all these x's, are all raised just to the first power, and there's no sines or cosines or exponentials or anything like that. So this is a linear system of equations, and we want to be able to solve them. So a solution to a linear system is giving numbers or whatever to x1, x2, and x3 so that it actually works. So how do you check that x1 equals 3, x2 equals -2, and x3 equals 4 is a solution? Well, you plug it in, right? That's how we show things are solutions. So we'll do the left-hand side. We get 2 times 3 plus 8 times -2 plus 3 times 4. That's plugging in 3, -2, and 4 for x1, x2, and x3 in the first equation. Then 3 plus 3 times -2 plus 2 times 4. That's my second equation. And 2 times 3 plus 7 times -2 plus 4 times 3. Right, so we just plugged in the numbers for x1, x2, and x3. You multiply them out. 6 minus 16 plus 12. 3 minus 6 plus 8. And the third line is 6 minus 14 plus 12. And that becomes -10 plus 12 is 2. 11 minus 6 is 5. 18 minus 14 is 4. 2, 5, 4. Oops. 18 minus 14. 2, 7, 4. Wait a minute. Well, made a mistake right out of the gate. This should be a 4 here, which means that would be a 16. And then I have 22 minus 14, which is in fact 8. Because this is my right-hand side now, if you don't make any mistakes. So this is a solution. Is it the only solution? We don't know at this point. We do not have an existence and uniqueness theorem for linear systems like we had for differential equations. We know that if you have a differential equation, you plug in the number and you get, you plug in the function and you show it works, then that has to be the only solution. But here we don't know that because we don't have any kind of existence and uniqueness theorem. So the solution set to a system of linear equations is a collection of all possible solutions. This is one solution to the system above. We don't know if it's the only solution. So the solution set, repeated the there, the solution set contains either no solutions, one solution, or infinitely many solutions. So we will see as we go through this that you can't have like 3 different solutions to a system of equations. 0 solutions, 1 solution, or infinitely many solutions. Now we solve these things by reduction. And generally what we can do with reduction is these 3 things. You can add 2 equations together and the result can take place of one of the previous equations. An equation can be multiplied by a constant, and equations can be written in any order from top to bottom. None of these steps actually change the solution set of a linear system of equations, right? Changing the order of equations doesn't change what the solutions are. Multiplying an equation by a constant that's not 0, or even if you multiply by 0, it doesn't change what the solution set is. Well, multiplying by 0. That should be a non-zero constant. And then finally, if you add two equations together, the solutions don't change, because if two numbers, if a solution satisfies each of two equations, then that same solution satisfies the sum of those two. So we want to solve this by reduction. So what do we want to do? First thing I'll do, is I will replace the second equation, equation 2, by 2 times it. I'm allowed to multiply by non-zero numbers. So, and that gives me this set of equations. Leave the top one alone. Multiply, oops, don't know what that is. It's a little annoying. So, and we're left with a 2 here. Multiply the middle equation by 2, that gives me 2x1 plus 6x2 plus 4x3 equals 210, and leave the third equation alone. And the point here now is all the x1s have the same coefficient. And that means I can get rid of the x1s in equation 2 and in equation 3. So I can replace equation 2 by equation 2 minus equation 1, and I can replace equation 3 by equation 3 minus equation 1. So when I do that, what do I get? I'm leaving the first equation alone, so that gives me 2x1 plus 8x2 plus 3x3 equals 2. Second equation, so 2x1 minus 2x1 is 0x1, and then 6x2 minus 8x2 is minus 2x2. 4x3 minus 3x3 is just 1x3, and 10 minus 2 is 8. Okay, now equation 3 will become equation 3 minus equation 1, so 2x1 minus 2x1, this is 0x1. 7x2 minus 8x2, that's a minus 1x2. 4x3 minus 3x3 is 1x3. And then 8 minus 10 is, 8 minus 2 is 6. Great, so let me put a little line here so we're clear about what we're doing. So these are my directions, and then I do that, directions, do that. So what's the next thing we want to do? I'm going to replace equation 2. I'm not going to replace it. I'm just going to multiply it through by minus 1 to get rid of the minus sign here. And then I will take equation 3. At the same time, I'll multiply that by 2. So we're leaving the first equation alone. So I have 2x1 plus 8x2 plus 3x3 equals 2. Multiplying the middle equation by 2, so that gives me, by minus 1, so it gives me a 2x2 minus x3 equals minus 8. And then multiplying the bottom row by 2, that gives me a 2x2 plus 2x3 equals 12. Right, and again, I'm trying to match the coefficients now in the x2. And so I can finish off my system by saying, let's replace equation 3 by equation 3 plus equation 2. And I'll zoom out a little bit so I don't have to scroll up and down to rewrite stuff. So we will take equation 3, and we replace it by equation 3 plus equation 2. So 2x1 plus 8x2 plus 3x3 equals 2. 2x2 minus x3 equals minus 8. Minus 2 plus 2 is 0x2. 2x3 plus minus x3 is just 1x3. When I add these two together down here, and 12 minus 8 is 4. Good. So we have now gotten down to this step. And what we've done this is we've done this by using these 3 rules, and doing those 3 things do not change the solutions. So the solution to this set, whatever possible solutions there are to this set of equations, are the same set of solutions as there are to this set of equations. So by reducing it, we get to a system of equations that's actually much easier to solve. We will at this point do something called back substitution. We know x3 equals 4, so that makes equation 2. So this is my x3 equals 4. There's one solution, one part of the solution. Equation 2 then becomes 2x2 minus 4 equals minus 8, because we're just plug in 4 for that. Or 2x2 equals, add a 4 to both sides, minus 4, or x2 equals minus 2. So using this solution, we can get the solution to this equation for x2. Using x2 and x3, which we now know, we can plug them back into the top equation and find out what x1 is. So we have 2 times x1 plus 8 times minus 2, because it's 8x2 and x2 is equal to minus 2, plus 3 times 4 equals 2. So 2x1 equals 2 plus 16 minus 12, 4, 6. So x1 equals 3. So there's our solution. It's the same solution we checked way up here, 3 minus 2 and 4. And now we know this is the only solution because we actually solved it. Okay, so reduction, pretty straightforward. I think you've seen it before when we've had 2 equations and 2 unknowns. You can do it for 3 equations and 3 unknowns, just try and get everything reduced down there. So note that the variables in the system don't play much of a role in the solution. The important thing with the numbers. And so to isolate just the numbers, we can represent the system as in something called the Augmented Matrix. So a system has got equations, equation 1, equation 2, equation 3, and variables. It's in the columns. And this, there's no real name for the right-hand side. We'll just call it actually right-hand side would be a good name for that. So let's just call this right-hand side. So what we'll do for an augmented matrix is we'll set up a matrix that looks like this. First row stands for the first equation. Second row is the coefficients of the second equation, 2, 7, 4, and 2, 5, 8. So it's the same batch of numbers arranged in the same way. We're just sort of suppressing the x's. So remember that this is the x1 column, this is the x2 column, this is the x3 column. 2, 1, 2, those are the coefficients on x1, 8, 3, 7, coefficients on x2, 3, 2, 4, coefficients on x3. And then this row is equation 1, equation 2, equation 3, a little bar, and then the right-hand side. So I just want to note here that some of the videos, I didn't put in the vertical bar. I don't think in context that would be a problem. But keep that in mind as we go forward. So this part is the coefficient matrix. This is a column vector, right? And it's just a bunch of numbers written in a column, and that's the right-hand side. So vectors are matrices with only one column, and we'll later generalize vectors and matrices. So parallel to the three rules of reduction are what are called three row operations that you can do on an augmented matrix. You can add two rows, right? And we saw that before. You can multiply rows by, I keep forgetting the non-zero constants. So rows can be multiplied by a non-zero constant. That's the same as the reduction that we did above. And you can switch rows around. That's the same thing as just switching around equations. So solve the system above by using an augmented matrix and row operations, and then back substitution. So we have the matrix, the augmented matrix 2, 8, 3, 2, 1, 3, 2, 5, 2, 7, 4, 8. So there's our augmented matrix. So we'll basically do the same thing we did with the reduction, but just with this matrix. Row 2, we will multiply it by 2. That gives me 2, 8, 3, 2, 2, 6, 4, 10, 2, 7, 4, 8. Now we've got all 2s in the first column, so we can, I should go right to left instead of up and down. We can replace row 2. We can replace that by row 2 minus row 1. And row 3, we can replace that by row 3 minus row 1. The idea is to get rid of these 2s there. So that would give us the first row staying the same. The second row now, 2 minus 2 is 0. 6 minus 8 is minus 2. 4 minus 3 is 1. 10 minus 2 is 8. Row 3, 2 minus 2 is 0. 7 minus 8 is minus 1. 4 minus 3 is 1. 8 minus 2 is 6. Great, so what do we want to do there? Well, we want to get rid of this minus 1 in the middle of the third row. So we will multiply R2 by minus 1 to clear out its minus sign. And then we'll make R3 go to 2R3. So that I've got 2s here. So leaving the first equation alone. And multiply the last equation by 2. Great, and now we'll take R3 and replace it by R3 plus R2, and that will get rid of this minus 2. So we have 2, 8, 3, 2, 0, 2, minus 1, minus 8. And then if we add these, 0 plus 0 is 0, 2 plus minus 2 is 0, minus 1 plus 2 is 1, minus 8 plus 12 is 4. Great, so there's that. And now we'll turn these back into equations. Right, remember that this is my x1 column, my x2 column, my x3 column, my right-hand side column. This is equation 1, equation 2, and then equation 3. So the first row here becomes 2x1 plus 8x2 plus 3x3 equals 2. Equation 2 then is 2 times x2 minus x3 equals minus 8, and that's at 2. And then finally, the last equation is 0 times x1 plus 0 times x2 plus 1 times x3 equals 4. Right? And in fact, this is exactly the same things we did up here, except instead of carrying the variables all the way through, we just dealt with the numbers. And this is actually kind of a useful way to deal with these things. Okay, so we ended up with this matrix at the end. So that's our echelon. It's called an echelon matrix because it's got this line here of numbers. Below it to the left, everything is 0. So echelon matrices have this rule: all rows of zeros at the bottom. We don't have any rows of zeros, but if you did have a row of zeros, you can always switch rows to make that on the bottom. And the first non-zero element of a row lies to the right of the first non-zero element of the row above. So this 2 is the first non-zero element in row 2, and it's to the right, one column to the right of the 2 there. This 1 is the first non-zero number in row 3, and it lies to the right of the non-zero number, first non-zero number in the row above. And echelon is this thing, you actually, if you look up geese in echelon rows, you see things like this. So every, if you had a row here, every goose is down and to the right of the goose above. So that's what echelon means. It's sort of in that form. Okay, so vector notation and algebra vectors. We mentioned that there are column vectors. And so the right-hand side of a system of equations is often a column vector. We have 3 components. Those are the 3 numbers. The vector is this. Vectors have little arrows on them. I often forget to put them there and sometimes just don't bother. So hopefully that will be clear from context. So what can we do with vectors? We can add them, we can multiply them by numbers, and we can reduce complicated vectors to less complicated ones. So in particular, suppose we take a vector v to be the vector 1, 3, minus 5. So that's a nice column vector. And we'll take a vector w, these are supposed to be arrows, equals, say, minus 1, 0, 4. So how do we add vectors? Just add the corresponding components. So it would be 1 plus minus 1, 3 plus 0, minus 5 plus 4. Right? And that's 0, 3, minus 1. So if you add 2 vectors, you just add the corresponding components. Now, if we have a number like 3 and we want to multiply it by my vector v, so that's 3 times 1, 3 minus 5. The 3 distributes to each one of the various components. So 3, 9 minus 15. So if you multiply a vector by a number, you have to multiply each component by that number. And of course, you can factor things out, right? If we had a vector minus 7, 0, 28, well, there's a 7 that's common to all 3 terms, so we can factor that out as a 7. Then what's left behind is minus 1, 0, and 4, and that's our vector w. So 7 times w is this vector. So we can factor out things that are common to all terms. And finally, let's see, I left myself not a huge amount of space, but suppose we have vector. So let's let S and T be numbers. We don't know what they are. Numbers. And suppose we have the vector S minus T 3s minus 5s plus 4t. So this is a vector, it's got 3 components. Can we break this apart? And we can break this into, because we can add vectors together, that means we can break them into different pieces. So I can take a vector that's got all the s terms in it, and then a vector that's got all the t terms in it. There's no t term here, but we can always think of that as 0t. So we're going to coefficient of 0 there. And now this vector has got s in common of all 3 terms. So we can factor that out. And we get 1, 3, minus 5. And this has got t in common to every term. So we can factor that out. And we get t minus 1, 0, 4. And so this is s times v plus t times w. So we can break things apart, put them together, multiply them by constants, add them, subtract them. So anyway, that's a little bit of thing about algebra vectors. We will generalize what a vector is and see things that are not column vectors later. So reduced row echelon form, what's that? So here's a matrix that we had above. We want to put it into reduced row echelon form, which is RREF. And so we'll do an example of that, and then we'll explain exactly what that means and why it's useful. So what I want to do here is I want to use the one that I have here to clean out those two, to turn those into minus ones. So what I'll do is I will replace R2 by R2, the second row by the second row plus the third row, and we'll replace R1 by the first row minus 3 times the third row. So I'm not actually going to multiply the bottom row by 3. I'll just do it in my head. You have to be a little bit careful sometimes when doing things in your head, of course. So I want R1 is R1 minus 3 times R3. So 2 minus 3 times 0 is 2. 8 minus 3 times 0 is 8. 3 minus 3 times 1 is 0. 2 minus 3 times 4 is 2 minus 12. So that's minus 10. R2 is just going to be R2 plus R3. So 0 plus 0 is 0. 2 plus 0 is 2. Minus 1 plus 1 is 0. Minus 8 plus 4 is 4. And then we left the bottom row alone. So what we've done here is we've got a 1 here and zeros in its column and zeros in its row. So we will take R2 and cut it in half. And that will give me 2, 8, 0, minus 10, 0, 1, 0, 4, 0, 0, 1. Right on the edge, good. Oh, and 0 there. Okay, so we want to clean out this 8 here. And so what I will do is I will replace R1 with R1 minus 8 R2. So 2 minus 8 times 0 is 2. 8 minus 1 times 8 is 0. 0 minus 0 is 0. Minus 10 minus 32. I may have dropped a sign somewhere. Oh, I did. That's a minus 4 here. Now that's a minus 2. Okay, so a minus 4 here, then I divide and I get a minus 2. So minus 10 minus minus 16 is 6. 0, 1, 0, minus 2, 0, 0, 1, 0. And so now this one is all by itself. There's no, just zeros in its column, zeros in its row. and we'll take R1 and replace it by 1/2 R2, and we get 1, 0, 0, 3, 0, 1, 0, minus 2, 0, 0, 1. Where's my brain going? That's a 4. I don't know why that's a 0. There we go. And if we turn this back into equations, remember, this is my x1 column, my x2 column, my x3 column. This is the right-hand side. I get x1 equals 3, x2 equals minus 2, and x3 equals 4, which is the solution, right? And so we've actually reduced the equation all the way down to just x1 equals something, x2 equals something, x3 equals something. So this is called reduced row echelon form, right? And has these 4 characteristics. So the echelon form, which means these, all rows of zeros at the bottom, first non-zero element of a row lies to the right of the first non-zero element of the row above. But we're also going to ask that the first non-zero element of a row is a 1, and that's going to be called a leading 1. So we've got a 1 here. That's the first non-zero element, another 1, and another 1. So each row starts with a 1. And these are called leading ones. All numbers in a column with a leading 1 are 0, other than the leading 1. So this first column has got a leading 1, so it's all zeros. This one's got a leading 1, so it's everything else is 0, not 0. So that's what reduced row echelon form is. We're trying to get everything to be just zeros as much as we can. So here's another example. We can solve this by using an augmented matrix and getting it down into reduced row echelon form, I believe is what we want to do. So let's set up, first things first, convert to an augmented matrix. 1, 1, 1, 7, 2, 3, 1, 18, minus 1, 1, minus 3, 1. So that's our augmented matrix. Remember that the columns represent variables and the rows represent equations, right? And we're just pulling out the coefficients, just pulling out the numbers. Okay, so we want to get rid of these 2 numbers, clear those out. And so we'll do that by row 2 can go to row 2 minus 2 row 1, because it's a 2, and if I make this minus 2, that'll give me a 0. And row 3 can go to row 3 plus row 1. Extend this arrow a little bit. Okay, so doing these options means I'm leaving row 1 alone. And now row 2, 2 minus 2 is 0. 3 minus 2 is 1. 1 minus 2 is minus 1. 18 minus 14 is 4. Remember that we're subtracting twice row 1 from row 2 there. Okay, and then row 3, we're just going to add row 3 and row 1 and use that as our new row 3. So if we add row 3 and row 1, what do we get? We get 0, 2, minus 2, 8. And to simplify things a little bit, since there's a common factor in the bottom row, we'll make row 3 go to 1/2 row 3. We'll extend this out so I can extend the arrow. We get 1, 1, 1, 7, 0, 1, minus 1, 4, 0, 1, minus 1, 4. Okay, so I want to get to reduced row echelon form. So what I want to do is use the middle one, this one, to clean out that and that, right? And then that'll give me a nice leading one in that column. So what I'm going to do now is I'm going to take row 1 and replace it with row 1 minus row 2. I'll take row 3 and I'll place that with row 3 minus row 2. We usually work left to right, clearing out columns. So I've got this column, 1, 0, 0. Row 1 is going to be row 1 minus row 2, so 1 minus 0 is 1. 1 minus 1 is 0. 1 minus minus 1 is 2. And then, move this up here a little bit, 7 minus 4 is 3. We leave the middle row alone, 1 minus 1, 4. And now row 3 is row 3 minus row 2. So 1 minus 1 is 0. Minus 1 minus minus 1 is 0. 4 minus 4 is 0. Right? And there's really nothing else I can do. This is in row reduced form. Row 0 is at bottom. Leading ones, and the leading ones, the column that the leading ones in has no other non-zero numbers. And then I have this column, which has no leading one in it. It is in echelon form. The first non-zero element in the second row is to the right of the first non-zero element in the first row, and there's no non-zero elements in the bottom row. So if we turn this back into equations, what do we end up with? X1 plus 2x3 equals 3. X2 minus x3 equals 4. And then the last equation is 0 equals 0. So there's our 3 equations. What are the solutions? Well, there's lots of possible solutions. I do want to address, though, real quickly, what happens if this was a 2 instead? How would that change everything? Well, if this was a 2, then this would have been a 2 here, right? And row 3 became row 3 plus row 1, which would make this a 9 instead of an 8. And then row 3 became half row 3, which would make this 4.5 instead of a 4. And then row 3 becomes row 3 minus row 2. And 4.5 minus 4 makes this 1/2 at the bottom. And that would give me here, instead of 0 equals 0, 0 equals 1/2. So I don't know what happened there. We'd end up with no solutions at all, right? Because if you get 0 equals to 1/2, there's no choice of x1, x2, and x3 that's going to make 0 equal to 1/2. So there's no solution at all to the last equations. So if we ended up with a row of zeros in the coefficient, but a 1/2 at the bottom, but a non-zero number at the bottom, then we have no solution. So what actually are our solutions? So every choice of x3 gives us a solution. So if we have x3 equals 0, that would give me x1 equals 3, x2 equals 4. And so this is a solution, then is x1 equals 3, x2 equals 4, x3 equals 0. So a solution means that we have to give a number to each one of the variables. So if we have x3 equals to 5, that would give me x1 equals 3 minus 10, which is minus 7, and x2 equals to 9. So that gives us another solution. X1 equals -7, X2 equals 9, X3 equals 5. And if you look at this, you can think of this a little bit as being a particular solution plus a homogeneous solution, right? X3 is a variable, it's a parameter, it's an arbitrary constant that we can change. And once we change it, we get new values for X1 and X2. The 3 and the 4, though, those have to stay. So we can actually rewrite this as in vector form. Any variable associated column that doesn't have a leading one is called a free variable, and that can be replaced by a parameter. So X3, the column for X3 here, oh, geez, that was a little ridiculous. The column for X3 here, which has no leading one, that means that X3 is a free variable. So we have we have X1 equals 2 minus X3. Was that correct? No, 3 minus 2X3. That's terrible. And X2 was equal to 4 plus X3. And we want solutions to be X1 equals something, X2 equals something, X3 equals something, and we don't want any of those three things showing up on that side. So what we're going to do is we're going to say, well, we'll add an extra equation. We'll say X3, well, I'm not sure I want to do it there, that's all. We'll set X3 equals to T, and this is a parameter or arbitrary constant. So if X3 equals T, and that's a parameter, that means it's just a variable that we can give any number to. We can make T equal to 5, we can make T equal to 0, make T equal to 318. Then what does that make X1, X2, and X3 equal to? So this is our answer, our solution vector. Well, X1 is 3 minus T, 3 minus 2T. So I replace the X3 with a T. X2 is 4 plus T. And then X3 is just T. And as we did above, we can break this into two vectors, one with the T's in it and one without the T's. So 3, 4, and then there's a 0 plus T in the bottom, and then minus 2T, T, T. Right, and that looks very much like a particular solution plus a homogeneous solution, right, which we've seen before in differential equations. So there's a solution vector. We've got one parameter there, and we had one parameter because we had a column that had no leading one in it. Okay, so here's a system of equations. There's actually only one equation. We can reduce the augmented matrix to reduce for echelon form, express the answer in vector form. So here we have our augmented matrix would be 4, 12, minus 8, 20. To get it to reduce for echelon form, we need to have a 1 in the first row. So we'll divide row 1 goes to 1/4 row 1. And that would give me 1, 3 minus 2, 5. So leading 1 and then 2 free variables. So our answer will generally have 2 parameters. Leading 1. Okay, so this isn't reduced row echelon form because there's only 1 row. So if we put this back into equation form, that's x1 plus 3x2 minus 2x3 equals 5, or x1 equals minus x1 equals 5 minus 3x2 plus 2x3. So we want our solutions to be in the forms of x1 equals, x2 equals, x3 equals, but x2 and x3, right? These two are free variables. So we need a parameter for this. We'll call this one s, this one t. And then what does that make x1? x1 is 5 minus 3x2, but x2 is equal to s. 3s plus 2x3 is plus 2t. And as vectors, 5 minus 3s plus 2t, s, and t. And then we can split this into 3 vectors. 1, which is just the constant terms, and then 1 that involves all the s's, and then we've got a coefficient of minus 3 and a coefficient of 1. Oops, minus 3, 1, 0. And then plus t, 2 t's here, 0 t's in the middle, 1 t at the bottom. And so there's our solutions. Every pair of numbers that you choose for s and t produces another solution. So we have infinitely many solutions here. So if you have a parameter, you usually have infinitely many solutions. For this one, we definitely have infinitely many solutions. Every choice of s and t gives you another solution. So we've been moving rows around. Can you move columns around? So here, these are the same, we just switched to the rows, right? And so as equations, they become this. Remember, this is my x1 column, my x2 column, this is my x3 column. This is 2x1 plus 3x2 plus x3 equals 18. x1 plus x2 plus x3 equals 7. Minus x1 plus x2 minus 3x3 equals 1. These are the same set of equations. And it doesn't really matter what order you write them in. So these augmented matrices have the same solution because the same set of equations, because all I'm doing is just writing the equations in different order. But if we look at this pair, now here we've actually swapped the columns. And that's my x1 column, my x2 column. So the first one is that. And here I have x1 plus x2 equals 7. But the second equation is 3x1 plus 2x2 equals 18. And so I've switched which coefficients go with which variables. Now, these are very different systems. Here we have x1 equals 3, x2 equals 4 is the solution, right? 3 plus 4 is 7, 6 plus 12 is 18. But here we have x1 equals 4, x2 equals 3 as a solution, right? 12 plus 6 is 18. So the solutions have switched around, right? And if we think of this as being on the x1, x2 plane, one solution is 3, 4, and the other solution is 4, 3. Right? So the order of the variables is important, so we can't really switch the columns around because then you're messing with the order of the variables. Okay, we don't want to do that. So finally, determining possible solutions for systems of equations by Rref. So by thinking about the reduced row echelon form of a system of equations, we can anticipate what sort of solution sets we can get. We either have no solution, and that's what happens when you've got a 0 equals 1/2, which we saw above. One solution, the first example, where we got all ones in it, or infinite solutions, and that was tied to the parameter. If the right-hand side is all 0, it's a homogeneous, same language that we used from differential equations. Otherwise, if the right-hand side is not all 0, it's non-homogeneous. So what are the possibilities for this solution set? So homogeneous means that here, B1, B2, B3, those are all 0. And a column vector that's all zeros is the 0 vector. So note that the row operations right? They leave a column of zeros as zeros, right? So what we can do with rows, we can switch them, but switching a 0 with a 0 doesn't change anything. We can multiply a row by a constant, but multiplying a 0 by a constant doesn't change anything. Or we can add 2 rows together. Adding 2 zeros together just gives you zeros. So there's always a solution to homogeneous. Right? 0, 0, 0, the 0 vector, that's always a solution to a homogeneous equation, right? If everything is 0, we can just leave that zeros. And this is called the trivial solution. If those numbers are not 0, if all of B1, if at least one of B1, B2, B3 is not 0, then you can have a different, you might have no solutions, you might have some solutions. So what are the possible reduced augmented forms for this? Well, you could end up with 3 leading ones. Right? And the B1, B2, B3 just will turn into 3 other numbers. We'll call them D2, D3. And here we have exactly one solution, right? X1 equals D1, X2 equals D2, X3 equals D3. Or you could have 2 leading ones. Right? We could have something like this. So we did the row operations. We got down to this reduced row echelon form. In the first column, we got 2 numbers, C1 and C2. The B's, after all the row operations, turned into 3 numbers, D1, D2, and D3. So there's 2 cases here. If D3 is not equal 0, this last equation here is 0 equals D3. And if D3 is not 0, that's just means there's no solutions. So a row of zeros in the coefficient matrix and then a non-zero number in the augmented matrix means you have no solutions. The other case is D3 equals 0, and that means that the last equation is just 0 equals 0, that's fine. And then that means we have infinite number of solutions because of a parameter. X3 is a free variable. So if you get down to reduced row echelon form, that's a free variable. And so that gives rise to a parameter. So you have infinitely many solutions. The problem is that you need D3 not equal to 0. If this was a homogeneous system, so we started with B1, B2, B3, then D1, D2, D3, they would all be 0. And so you'd have infinitely many solutions. So this 3x3 matrix can have either one solution or no solutions or infinitely many solutions. What about this one? So here we have two variables, x1 and x2, and a right-hand side, and we have three equations. And again, if the right side, if homogeneous, trivial solution is a solution, but we don't know whether or not it's the only solution. If it's not homogeneous, then we have to be careful. So what kind of reduced row echelon forms we can have? We only have two columns, so you can only have at most two leading ones. And so we could have, as its reduced row echelon form, we could get one leading one in that column and a leading one in this column. And then we get D1, D2, D3. And then there's two cases. If D3 does not equal 0, there's no solution, right? Because if that's not equal to 0, our last equation is 0 equals D3, there's no solution there. And if D3 does equal 0, then we end up with one solution. And that's x1 equals D1, x2 equals D2. Two arrows bonking into each other like that is a sign for a contradiction. So 0 equals D3. If D3 is not 0, that's just not possible. But you could also have just one leading 0. And here we need you would need D2 and D3 to both be equal to 0. So you need a full row of zeros there. And then you have a parameter . Right? Usually when you have more equations than unknowns, you end up in this situation with D3 not equal to 0 and there's no solution. That's usually what happens. The numbers have to be chosen very carefully so that you actually get a solution. And then example 11, here we've got three variables, x1, x2, x3, but only two equations. We could have, for a reduced row echelon form, we could have two leading ones, one in each row. And that would definitely give us a parameter. And this would turn into D1 and D2. And we end up with infinitely many possible solutions. That's usually what happens, but sometimes you could have a reduced row echelon form where you just have one leading one, so a 1 and a 0, and then a C1 here and a 0, and a C2 there and a 0. And then a D1 and a D2. And here again, you would need D2 not equal to 0 to have any solutions. No, backwards. D2 not equal to 0 means no solutions. D2 equals 0 means infinite solutions because you actually have two parameters, one for x2 and one for x3. Excellent. And then that's that lecture.